So I'll actually be presenting on behalf of Mohammed Elbaz, who couldn't make it today, about 4D hemodynamic signatures. So we're aware that 4D flow gives us a very rich data set, and it's a velocity field, a vector field that's resolved temporally as well. And we were looking for a new metric that would allow us to take into account all of the data, both temporally and using a vector-based method. And so the method used here to develop this metric, or this velocity signature, is to randomly sample 2 points in space and time and compute the vector difference in the velocities. Then we can compute the magnitude of this vector, and we can perform the sampling many, many times and compute a probability density function like shown here. And this allows us to work directly with the vectors. And we did this in 338 subjects, 209 of which were bicuspid aortic valve patients with left-right fusion pattern, and 129 who were healthy controls, all at 1.5 Tesla. And we can see here if we compare controls in gray to bicuspid aortic valve patients in red, and this is possible because it's a probability density function and is normalized to 1 already, so we can compare without any registration or any other manipulation of the data. We can see that there's a clear difference between controls and BAV patients. And we can take this one step further. We can actually look at the valve status of these patients, and we can compute a dissimilarity metric between these curves. And we can see that we can actually stratify these patients based on their aortic regurgitation and aortic stenosis status. And we also see a very clear difference between patients and controls here as well. So we're hoping that this is an exciting new metric that we can use in patients going forward. So if you want to hear more, come to the poster. Thanks a lot.